Hello everyone, myself Amulya. Today we will be discussing about the topic most common and critical challenges in advanced machine learning handling imbalanced data by our team members and me, Vaishnavi Reddy, Amulya, Fatima Armain and Srushti SS. So the first slide focusing on the problems and the bias. This section defines the core issues. The imbalance problem. A dataset is considered imbalanced when one class significantly outnumbers the other. For example, in fraud detection, legitimate transactions, the majority class vastly outnumber fraudulent transactions, and the minority class. Model bias. The imbalanced datasets can cause ML models to be biased toward the majority classes. This makes the model poor at detecting the crucial minority classes. Example, fraudulent transactions. The result, a model might achieve high overall accuracy, example 99% of samples, simply by classifying everything as a majority class, making it practically useless for the intended purpose of minority class detection. The second slide, the data preparation steps. Proper data preparation is crucial to ensure the model can generalize well and isn't influenced by data scale or missing values. The three steps mentioned are dataset selection. Firstly, dataset selection. In the context of imbalanced data, this involves selecting a dataset whether the minority class is represented by the key observations of interest. For example, fraudulent transactions. The second step is about the data processing. Data pre-processing. This involves cleaning the data by removing unnecessary columns and handling missing values, imputing of removal. Then the third one is splitting and normalization. Splitting is dividing the dataset into training and testing sets. Typically, 80 to 20 splits are common. Then normalization or scaling, adjusting the numerical features to ensure they are on similar scales, preventing features with large values from dominating the model training process. The next slide will be continued by.
Hi, myself Rishvi. I'll be explaining training without imbalance handling. This slide explain what happens when we train a model without handling class imbalance. In imbalance dataset, the model tends to focus more on the majority class and ignores the minority class. For example, in fraud detection, it predicts the most transactions as normal. This leads to high overall accuracy but very poor recall for the minority class, meaning it fails to detect many fraud cases. So even though the accuracy looks good, the model performance is actually misleading. And the next slide is evaluation matrix beyond accuracy. That's it. Its precision tells us how many of the predicted positives were actually correct. Recall or sensitivity shows how well we identified the actual positives. F1 score gives a balance between precision and recall, and ROC and AUC measures how well the model separates the classification classes overall. These matrices give a such clear and fair picture of how our model is truly performing.
Explaining applying resampling techniques. Resampling techniques modify the dataset to make both classes more balanced. We have two common techniques. One is oversampling and second one is undersampling. Oversampling creates synthetic samples of the minority class instead of simply duplicating them. Example is a SMART. SMART means synthetic minority oversampling technique. This increases the number of minority class examples, helping the model learn their characteristics better. SMART works by generating new samples based on the nearest neighbors of existing minority points. Its goal is to increase the minority examples, helping the model learn their characteristics better. And second one is undersampling. Undersampling reduces the number of majority class samples so that both classes have similar sizes. This method helps to balance data quickly to might remove potentially useful information, and the goal is to balance the data quickly but risks removing potentially useful information. And the second slide, retaining and expected effects. After applying both smart oversampling and random undersampling, the classifier is retained on each modified dataset. The purpose is to observe how resampling affects model learning and performance, and to check whether the model becomes better at identifying minority class samples. Expected effects are in oversampling. It increases recall and F1 score as the model gets more minority class examples. Its accuracy might slightly decrease due to added synthetic samples but becomes more balanced. In undersampling, it improves recall but might reduce precision and accuracy since some majority class samples are discarded. The model learns faster due to smaller dataset but may lose information.
Yeah, here I'm explaining about the comparison of results. Thus, resampling significantly improve minority class detections, with SMART showing the most balanced performance. Here we have a three model types. First is original model, SMART oversampling, random sampling, and in accuracy, original module has a high accuracy and slightly lower in oversampling and completely lower in the undersampling. Precision is moderate in original model, then in high in oversampling, moderate in undersampling. The recall is very low in original model and high in oversampling and undersampling too. Then F1 score is low in original model, uh, in oversampling and is high, and even in undersampling it is moderate. Then recall and F1 improved dramatically after resampling and validation with the approach. Uh, and we have why the smart is the best technique means it is a synthetic generation generates a realistic synthetic samples, improving a class balance without simple duplications. Data retention retains all majority class samples, preserving values information, and undersampling discards. Supervisor matrix best in F1 and ROC and RUC graphs, scores, indicating overall improved classification performance. And the conclusion, here is the conclusion. Building a robust models. Handling class imbalance is a critical step in building robust machine learning model. Resampling methods significantly enhance a model's ability to detect the minority classes, which are often the most important in real world scenarios. Among the tested techniques, smart oversampling is produced the best performance, improving the recall and F1 score without drastically affecting the accuracy. And it enhanced detections like resampling methods, particularly oversampling, significantly enhance model ability to detect the minority classes. Then, thank you.
We are explaining about the handling of imbalanced data sets. Here is the data which we are using in a CSV file. These are the files we are used. Then coming to the main code, uh, at first we are importing the operating system, then pandas, sklearn of model selection, pre-processing, linear model matrices, and oversampling, undersampling. In the step one, we load and prepare a data from the line 14 to 20 second. Then we split the data information into a features and a target as a feature as a x and target as a y. Then we split that features and the target data into train and split data. Uh, then we standardize and scale the features. In the step two, we train the original model by the logistic regression for a original model. And in step three, we are applying a resampling. There is a oversampling with smart, then undersampling for a random undersampling. Then we in step four we are retrain models like by oversampling sample model and a sample model by logistic regression. Then evaluating the matrices. Next in the step five we are evaluating the matrix. Uh, Results are there is accuracy, precision, recall, F1 score, and ROC, AUC, which we will train and the test data. Then we save and display the result. Here is the output. At first, dataset has a accuracy, precision, recall, F1 score, ROC, and AUC. Original data accuracy is 0 and oversampling is 0 and random undersampling is 1. Precision is 5, again in oversampling also 5, undersampling is 1. So this is the result.